Hi, folks. We had some technical difficulties today, so I'm recording this. I'll put it up as soon as I can get enough bandwidth and a stable enough connection to upload it. But I did want to make sure we have a quick discussion about lines. Lines in general should be something that you're pretty familiar with, pretty used to working with. Most of this chapter 2 stuff online that'll cause you some trouble is with the word problems. They will take some practice, and I do encourage you guys to send me those or make note of them so we can look at them in class. I do like the opportunity to discuss word problems together with you guys. And hopefully we'll get a chance to do that next week. But I did want to talk about the mechanics of equations of lines together a bit, just to look at it from maybe a different perspective. We've been talking about that idea of average, turn this, average rate of change. And for average rate of change, we used that formula. It might have looked a little different than we're used to, but I reminded you guys that this is really just a formula for slope. It looks a little bit different because it's in function notation, but this is really just changes in y's and changes in x's. The reason this formula is a little bit different, and the reason it's not just called slope, is because it is made to be used with any type of function. It doesn't have to be a linear function. It can be any abstract function, and it will allow us to discuss the average rate of change between any 2 points by looking at the slope of that secant line passing through those 2 points. Now, the reason it's average rate of change between a couple of points and not just the function's rate of change is because, as I'm sure you can imagine, if we change the 2 points that we're talking about, we're going to get different rates of change depending on where on this curve we look. So it doesn't have a constant rate of change. This average rate of change is going to be different depending on where we are. Well, the one thing that makes lines special is that their average rate of change, their rate of change, is constant. So if we gave ourselves, let's say, I don't want it to be blue, or not light blue anyway. If we gave ourselves a nice big graph with a nice line on it, oh, there we go, with a nice big line on it, and say we knew some points on this line. So let's say, oh, we knew, I don't know, -5, -2 was on that line. And say we know this point is, oh, where's that going to be? How about -2 and 1? And let's say we know this point is, gotta get this right, 1 and 4. So let's say we know this line has those 3 points on it. Well, if we wanted to find the average rate of change, if we wanted to find, use this formula to find the rate of change between this point and this point, versus finding the rate of change between this point and this third point, or even the rate of change between just these two, all those rates of change would be the same because the slope is the same. And we can even do that if you want to. And we will. We'll actually do that with a couple. But when we talk about slopes, we still, we'll use that y2 minus y1. Again, y2 and y1 is really the same as f at x2 and f at x1. It's just this is in function notation, where this is in equation notation for our x and y axis. But that difference in y in ratio to the difference in x, what makes a line special is that this value, the rate of change or the average rate of change for any points is always the same number m. Here it would be different depending on what values we pick. You pick a different x1 and x2, and the rate of change is going to be different depending on whether the function's increasing or decreasing or whatever it's doing. For a line, that slope is always the same because the amount that it's increasing or decreasing, if the line's going downward, that amount is always fixed. So if we did this and picked any of these for x1 or y1, let's label these. Let's say this was x1, y1, and we let this be x2, y2. It is handy, by the way, to label these if you're doing them. It just helps you keep the numbers straight. It's a good habit. So if we used those points, we would have, let's say, 1 minus -2 over -2 minus -5. So we'd have a slope of, what that would be, 3, and that would be, -3. So I guess our slope would be -1. Nice. Oh yeah, that makes sense. So we'd have a slope of -1. If we instead chose a different pair of points, let's say we didn't use that point and instead used this point as our x2, y2. If these are all on the same line, we call them collinear. If they're on the same line, collinear, then that slope should be the same. So it would be, what, this time it would be 4 minus -2, and use the right one, and 1 minus -2, right? 4 minus -2, and 1 minus -5. That felt wrong. Ever have that happen where it just feels wrong? Minus -5. Okay, that's better. So then that'll be 6 over 6. Oh, duh. That was a +3. This is a +1. Obviously, this line is going upward, right? So that should have been a +1 slope. It's always nice to catch those mistakes. It's hard when I don't have you guys here to say, Mr. H, that should have been a +1. That's why I like having you guys around. So we do get, with that correction, that same slope of 1. Again, even if we did it with these other two, and I do want to take a moment and do that, even if we didn't use this as y1 or x1, y1, we use this as x1, y1, we will still get the same value because these are all on the same line. So our slope, m, is, what, 4 minus 1 over 1 minus, this time it is -2. So that's 3 over 3. It's still 1. So no matter what those points are, as long as they're collinear, as long as they're on the same line, that slope is always the same. That's, again, what makes a line special, is that constant change, a constant amount of change, that constant slope. So if our goal is to make an equation for this line, what the equation of a line is supposed to do, its job, is to give us a rule that defines every single one of these points on this line. Remember, that's what a function really is. A function is a way of defining every single one of these ordered pairs, every single point x, y, or x f of x, if you prefer. Every point x, y on this line, I want a rule that defines all of them. Because trying to list all of the points out one by one would be an infinitely long list. It would be a pointless exercise. We'd never finish writing them all out. But if I can write a function, write a rule that links every x and y point together on this line, well, then I don't have to list them all out because my function, my equation, if you want, will have all of them contained in it. So to do that, one of the things that we can do is just use this same tool. We can pick any one of these points to be kind of our anchor point. And again, we'll use the orange. Again, let's use this one. Doesn't matter which one we use. Let's use this one. So I'm going to call this our x1, y1 again. But instead of using one of these points as our x2, y2, I'm going to use this generic xy. So this is essentially our x2, y2. Now notice this notational difference. The x1, y1 is a label for this particular x value and its particular y value. When we had this as x2, y2, the x2 was this particular value. Down here, this x and y is the generic x and y that's labeling every point on this line. So we're not going to get a specific set of values here. This is our generic xy that is supposed to stand for every single point on this line kind of at the same time. But what do we know? We know if we take the difference between the y values, if we take the generic y value, again, any one of these, generic y value, and subtract that y1, the 1, and divide that by this generic x minus our x1, the x minus the x1, we will get that same slope that we've been getting this whole time. And that slope we've been getting the whole time has been a 1. Now, as odd as this might look, I mean, we could clean this up a little bit. 1 equals y minus 1 over x plus 2 if you want. But this really is an equation for this line. It is a rule that links every xy pair that is on this line. Every xy pair, when put in this formula with using this x1, y1 as an anchor, every xy pair on that line will give us a 1 for a slope. And if we'd have picked a different x1, y1, if we'd have picked the 1, 4 or the negative 5, 2 and changed this to the, the negative 2 and the negative 5, then every xy pair still has to give us a 1. So this rule works to define every single one of these points. And if somebody asked you, give me an equation for this line, this would work. It might not be what they expected. It might not look like how we expect it to look, but this truly is an equation of a line. You put an x value in here, it will find the corresponding y. You could solve it. But because this looks a little funny, why don't we clean this up and make something that might look a little more familiar? So to do that, I'm going to multiply both sides of this by x plus 2, because I don't like having that x plus 2 in the denominator. Those will then cancel. And this side will just be y minus 1 equals, I'm going to move this stuff to the other side, that 1, again, that's our slope, times that x plus 2. Now again, that leaves us with an equation where if you put an x value in, you'll get a y value. This relationship still defines every xy pair on that line. And you might have seen this form of a line before. Oops, sorry. You may have seen that form of a line before. It would have looked like y minus y1 equals m times x minus x1. That's really what we have here. Our slope is right here, our 1. Our y1, so y minus that y1, and x minus the y2, remember x minus the x1. That x1 was, remember, -2, so that x minus -2 turned into x plus 2. But this form of a line is really just this slope formula modified so it looks a little bit more like an equation. Some of you have hopefully used this form before. It was often referred to as the point slope form of a line because it contains a point, x1, y1, and the slope m. So this is actually a good tool for building lines. Often we don't want to start in this form and work from this formula to build an equation of a line. So oftentimes we'll start here. And frankly, you often see people modify it a little bit more. They'll add this y1 to both sides and get m times the x minus x1 plus y1. I don't know why I changed that to a cursive looking y or a funny looking y. y1. Because, what's the first thing we're going to do up here? We'll probably add that 1 over. So we'll talk more about this in a minute, but that point slope form of a line is really, really, really handy. But getting back to this, we certainly could distribute that 1. It would turn that side into just x plus 2 equals y minus 1. Add that 1 over, plus 1, and y equals x plus 3. And that's the equation of our line in a form that we're probably more familiar with. It's got that slope of 1 that we could write in there if we wanted to. It looks horrible, but we could if we wanted to. So that's our standard y equals mx plus b form of a line, where still m is that slope, b is the y-intercept, so that actually tells us this point here is the point 0, 3. But getting there from this idea of slope, I think it's really helpful to notice that both of these forms are just consequences of the idea that this ratio, that this slope, is a constant m. So one of the things that this form, and either one of these, this point slope form, is really useful for is kind of doing this, is building the equation of a line when we have a couple of points. So let's say, for example, we're told we have 2 points, let's say 3, -1, and 8, 4. And you want to find the equation of the line between 2 points. Being able to find the equation of a line 2 points is the equation of a line between 2 points is an important skill. So make sure you practice it. It comes up on quizzes, tests, other courses, other types of problems a lot. So make sure you practice this. But if we have 2 points, what we can do with those 2 points is, like we did with these points, find what that slope is. So we grab that m equals y2 minus y1 over x2 minus x1. And again, by habit, it's a good habit to be in, I'm just going to label these real fast. It takes like 5 seconds to do, but helps avoid little irritating errors. So taking a moment to label those real fast will help everything stay straight. So that slope m equals, the y2 was 4 minus the -1 over x2 is the 8 minus, did I get a slope of 1 again? Up 5, down 5. Ugh, I don't want a slope of 1 again. Let me come up with new numbers there and not get a slope of 1. What do you say? Can't do it twice with that. So let's say 7, -1, and, oh, 9, 5. There we go. That's going to be a better slope. So we want to do the same thing. We want to find that slope. Again, I am going to take that moment and label them. It just stops me from making irritating errors with pluses and minuses. Every time you get frustrated, when you make a sign error, think about labeling stuff and trying to help yourself make those less. So 5 minus -1 over 9 minus 7. Let me check that. 5, -1, 9, and 7. Good. Is going to give us a 6 over 2, or a nice slope of 3. Gosh, we're really avoiding fractions today. Make sure you practice those fractions. So we have a slope, m equals 3. In case you're curious why we use m for slope, it is the first letter of the French word for ascend or to climb. I think it's monter, the same root word as mount. So an ascending line, the ascension rate, that's why we use m. It's from the French, because I know you were wondering. So this slope of 3 tells us what our slope is. And if we grab either of these point slope forms down here, I'm going to grab this one down here, we can build our line just by going y equals that slope, m3, times x minus x1. Well, our x1 was 7, plus y1. Well, our y1 was -1, -1. And that's the equation of our line. We could stop there. You probably know we're not going to stop there. We could clean this up a little bit, but it makes for a really fast way, really a super efficient way to make the equation of a line that tends to be really quick, really accurate, really stable. I know a lot of people like to use some of the techniques to only have to use this form by kind of solving for this b term, and you can do that. It works. It works fine. But it does tend to lead to certain types of errors if you're not super careful, and it does tend to be, frankly, slower over time. About the major reason I see people resist using this form, using this point slope form to build a line, is just because they don't want to have to memorize another form. And I try to encourage you not to do that. Don't memorize this form. You already know the key. You know this slope formula. This point slope form is just this slope formula with that x2 minus x1 multiplied over. That is foundationally your point slope form. We just make that second xy pair an abstract xy, and boom, we have point slope form. Adding over that y1 is nice if you want the really quick form, but it's not really memorizing a new tool or a new form. It's just manipulating what you already know to get a really nice tool to build the equations of lines really quick, really accurate. I encourage you to practice it this way some. If you end up using the, kind of mx plus b, solve for that b methodology, it's fine. But the more you see this, the more you have to build equations of lines, particularly those of you going into calculus, you will tend to start moving towards this method. And I encourage you to try to make that switch sooner rather than later. Okay, we'll talk about some of the linear word problems in class. I just wanted to give you some of this kind of perspective on what really makes lines lines and what this equation is, and where some of these tools come from. So if you have any questions on that, bring them to us in the Zoom, or send me an email or a message. And if you have any questions on anything, let me know. I'll see what I can do to help, and have a wonderful day.